This is problem 3.2-8 from the book Conceptual Dynamics. And so again, the way that we always start a problem is to read it carefully and to draw a picture if necessary. In this case, the picture is provided. But what we have here is we have a projectile motion problem. And so if you recall, the way that a projectile motion problem works is that our particle is given some initial velocity and then it's let to fly through the air on its own. And in general, we will neglect air resistance as it's flying through the air. And so if we read the problem, it states that it tells us that the initial velocity of the ball is 30 meters per second and that it's thrown at an angle of 40 degrees above the horizontal. And it asks us to find the maximum height h, the time it takes the particle to reach point C, and the total horizontal range that the particle travels. And so once we've read it and we feel like we understand it, we try to figure out what's given and what's unknown in the problem. And so when we do that, we also want to set up a coordinate system and state any assumptions. The assumption here is that we will neglect air resistance. And so as the particle is flying through the air, the only force that's acting on it is its weight. And so that means that the acceleration of the particle will always be g in the negative y direction. The coordinate system is set up for us here. We have y vertical and x horizontal with the origin at the beginning location of the particle, which we've defined to be point A. Oftentimes, this sort of Cartesian or rectangular xy coordinate system is well suited to a projectile motion problem because it allows for the acceleration to be entirely in the y direction and that there be no acceleration in the x direction. Looking at this, it's sort of a standard projectile motion problem. We start at point A. It's defined the apex to be point B, and then the final location of the particle's trajectory is point C. Something interesting to note is that the particle ends up 10 meters below the height at which it was launched from. So reading the problem, we can identify that we're given that the initial speed of the particle is 30 meters per second, and that its initial direction is 40 degrees above the horizontal. And so together, those two quantities give us the magnitude and direction of our velocity vector. We can also express a vector in terms of its components, in terms of its x component and its y component, because we're using an xy coordinate system in this example. And so that is helpful to do in this case and in projectile motion problems in general, because we often will take the approach of breaking down the problem into doing the analysis for the x direction and doing the analysis for the y direction separately. So looking at this, the x component, if we are imagining a right triangle here where the velocity vector is the hypotenuse, the x component is the side adjacent to the angle. And so if we think about SOHCAHTOA, the adjacent will correspond to cosine. And then for the y component, that side is opposite the angle. And so for opposite, we use sine. So that's information that we're given. We also have some other things we know, that the acceleration in the y direction is minus g. We know that the acceleration in the x direction is 0. At the apex, we know that the y component of the velocity will be momentarily 0. So we can sort of imagine that on the way up, the particle has a positive y velocity. On the way down, has a negative y velocity. And so for a split second, at the apex of its trajectory, its y component velocity will be 0. We know the initial position in the y direction and the x direction. It starts at the origin. And then we know at point C that the particle is 10 meters below the origin, 10 meters below the x-axis, and so its y position is minus 10 meters. So that captures pretty much everything we can kind of glean from the problem. We can see that we're asked to find the height, which in essence is the y position at point B at the apex. We're asked to find the time it takes to reach point C, and we're asked to find the horizontal range, which is basically the change in the x position. So with that, we can go ahead and start the problem solution, which, as I said before, we will tend to separate into an x part of the analysis and then the y direction part of the analysis. So in general, we can really start with either the x direction or the y direction analysis. Oftentimes, I'll choose to start with the x direction because it's the easier of the two. And so if we look at what we're given that's relevant to the x direction, we have the initial x direction velocity. And an important thing to remember is since the acceleration in the x direction is 0, this velocity will be constant. That will be the x component of the velocity throughout its entire travel. We were also asked to find change in the x position and the total time of flight. The other elements that were given are really only relevant to the y direction. So we'll start with those. We may not be able to solve for everything that's asked for here, but that's okay. We'll go ahead and go through the analysis and set up the equation, and then we can save that and use it later. So looking at what is given and what is unknown, and looking at our sort of three basic equations in order to try to connect what is given to what we're trying to find, it looks like this first equation is the best bet. It has what we're given, and then it has what we're trying to find, the time in the air and the change in the x direction position. And so we can take this and we can rearrange it. So we can multiply that dt over to the left-hand side. So we have Vx on the left, multiplying dt, we're left with dx on the right. We can integrate both sides. We can take advantage of the fact that Vx is constant. So it's the same as the initial. We can say that the initial time is time equals 0, and then the time when it reaches point C is t sub c. On the right-hand side, we integrate with respect to x. Based on our coordinate system, again, we say that the initial x position is 0, and then the final y position at point C is L. Since b sub x 0 is constant, its antiderivative will just be that multiplying t. On the right-hand side, it's sort of like there's a 1 in our integral, and the antiderivative of that will just be x. And so this is a sort of a general form of the equation. If we evaluate it at our specific limits, t sub c, and our final position x, then we get that v sub x0 times tc equals L. And so this is kind of our result. We know what v x sub 0 is. We don't know what tc is, and we don't know what L is. So we have only a single equation, but we have two unknowns, so we We can't solve it at this point. But I'm going to go ahead and save it and call it equation 1 um, because it is something that we will be able to use later. So we will come back to that relationship. Now we can move on to the y direction analysis. And so looking at what we were given in the problem, we know what the initial velocity is, we know what the velocity in the y direction is at the apex, and we know what the initial and final y position are. And these were the two things that we wanted to find. We wanted to find the y position at point B, and we wanted to find the time of flight. Let's go ahead and start with the first unknown, h. And so if we do that, if we look at what we're given, and again, we want to sort of remember that we know what the y component of the acceleration is. If we look at what we're given and we look at what we're trying to find, of the three equations, the third one has everything that we need. So we know the acceleration. We are trying to find the change in height between A and B. So that's the unknown. And we know the velocity, its initial velocity and its final velocity between those 2 points. So this third equation has everything we need. It doesn't include time, which we don't know. So that's a helpful thing. So taking this, we plug in for the acceleration. On the right-hand side, we have velocity. We integrate both sides. And so in terms of the limits of y, we know that we're starting at a height of y equals 0, and we're ending up at a height h. That's the unknown that we're trying to find. On the right-hand side, we know what the initial velocity is. It's given. And we know at the apex that the y component of the velocity is 0. We then, remember that minus g is a constant. And so if we take the antiderivative of that, it's negative gy. On the right-hand side, we take the antiderivative of vy with respect to vy. And so the antiderivative there is we add 1 to the exponent. We get an exponent of 2. And then we have to divide by the 2 to cancel that exponent, when we take the derivative. So that is true in general. If we evaluate it between the two limits, we have that and that. On the left-hand side, we have minus g times h. On the right-hand side, when we sub in the upper limit, we get 0, and then we subtract the expression with the lower limit substituted. And so we get that. And then if we want to solve for the unknown h, on the left, we have v sub y 0 squared times 1/2. We divide through by g. That ends up in the denominator. We had a negative on the right, and we divided through by a negative g. So the negative divided by the negative just turns into a positive. And so this is our expression for height. We can plug in what we know. So we know that the initial speed is 30 meters per second. We know that the y component we get by multiplying by sine of 40 degrees. We square that quantity. G in meters per second squared is 9.81. We punch all of that into our calculator, and we get that the height is approximately 8.95 meters. And so, again, it's always good to carry our units through. So as a kind of a double check that we're using the right equation, a sanity check. So in the numerator, we had meters over seconds, and we squared that quantity. So in essence, in the numerator, we had meters squared and seconds squared. In the denominator, we had meters per second squared. And so the seconds squared cancel. Um, one of the meters squared cancels with the meter in the denominator, and so we're left with the total units of meters, which is what we should end up with. That is the height of the particle. Height is in meters. So that gives us one of our unknowns. Um, in this problem so far, I've been doing everything in terms of these sort of basic derivative and integral equations. And that's sort of how I like to do things because it's the most general. If you are more comfortable doing so, you could also use the constant acceleration equations because in projectile motion, we do have constant acceleration. That is not true in general, so just be careful about using those. So that's just another point to take home. Now we can attempt to find the other unknown, the t sub c. Again, we can use our y direction analysis. If we look at this, this third equation doesn't have time in it, so that's not going to be very helpful to us. So we can look at these first two equations. So the first this second equation, if we look at it, we know what the acceleration is. That's negative g. It has time in it, which we're trying to find, and it has velocity. And so we know what the initial velocity is, but we don't know what the final velocity is. So there's kind of a little bit of a piece missing there. With the first equation, again, it has time, which we don't know. It has the change in position, which we know. We know the initial position and the final position in the y direction. But we don't really know, we don't have an expression for velocity over the entire flight. So these two equations, on their own, we don't have enough information to use either one. But what we can do is we can combine them. So first, I'll start with the acceleration equation. And so I have a sub y. Again, I can take that dt and multiply it to the left-hand side. On the right-hand side, I have dvy. Integrate both sides. In this case, I'm going to do it sort of generically. So I'm going to get a generic expression for v sub y. So I know what my initial velocity is. I don't know what my velocity is elsewhere. So I'll just have a variable for the upper limit. For the time, I know that it'll start at time sub 0, and I'm going to leave sort of a variable time as the upper limit. And so when we're done with this, we'll get an expression for velocity, which we can then plug into this first equation. So the thing we have here is we know that the acceleration is minus g. Since it's a constant, we know that the antiderivative will just be that constant times t, evaluated between 0 and t. On the right-hand side, it's like we have a 1 in the integral, and so the antiderivative of that is just the variable vy. And we evaluated it between the initial velocity and some variable final velocity. And so on the left, I have minus g times t. On the right, I have v sub y minus v sub y 0. If I rearrange, I can add the v sub y 0 to the other side. And there I have an expression for the y component of the velocity throughout its flight as a function of time. Once I have that, I can then go ahead and plug that in to this first equation. So I'll bring that down here. I'll multiply through by the dt. integrate both sides. And so something that you need to be careful about, that Vy is not constant. As the particle is flying through the air, the y component of its velocity is changing. And so that's a common kind of mistake. Luckily, we can, I'll call this equation 2. We can sub in our expression that we just found for velocity. It's v sub y0 minus g times t. We integrate that with respect to time. And we have on the right-hand side. And so we can evaluate that between, we'll go ahead and leave it as a variable for now. So we'll leave it as 0 and t, and on the right-hand side, I'll say 0 and y. And so the antiderivative v sub y0 is a constant, so it just becomes that constant times t. That negative g is a constant, so that, in essence, could come out front. The antiderivative of the t will add 1 to the exponent, and then we have to divide through by 2 to cancel the exponent when it comes down. And on the right-hand side, we have y. And so you might recognize that as one of our constant acceleration equations. And so in general, any of these, when we go through them, we can derive back those constant acceleration equations. If I plug in, at point C, I'm going to go ahead and move everything to the right-hand side. So that negative 1/2, I'll add to the right-hand side. It'll become positive. I'll subtract the v sub y0 t. And just to remind us, that is v sub 0 times sine of the angle times t. And then already on the right-hand side was y. And at point C, that is minus 10. Y is equal to minus 10. And I'll go ahead and identify that the time is at point C. So what we have here is we have kind of a quadratic equation. And so we know how to solve for quadratic equations using the quadratic formula. So if we remember, it's minus b, which in this case becomes positive v sub 0 sine of theta, plus minus the square root of b squared minus 4ac. So this first term, this 1/2 g, is the a, and then the c is the minus 10. And then we divide through by 2 times a. And so that is our quadratic formula. We have all of the numbers to solve this. So if we go ahead and plug in, we get that t sub c is equal to 1.96 seconds plus or minus 2.43 seconds. And so, in general, when we have a square root like that, we have a positive root and a negative root. We have the plus and the minus. And so when we do that, sometimes you sort of have to use your logic, your common sense to figure out which of the two roots is the one that is real. And so if you look at this, we will have a negative root and we will have a positive root. And so if we go back to sort of our picture, the trajectory of our projectile, it ended up at a height lower than it started. And so mathematically, the positive time is going to be the time when we reached point C. The negative time would sort of be like if the projectile went backwards in time across the same sort of parabola, and that's what it when it would have hit the ground, the negative 10 meters if it was going backwards in time. Obviously, we don't go backwards in time, so we're only going to take the positive solution. And so in this case, the positive solution is 4.39 seconds. So that is one of the unknowns that we wanted to find. The very last thing that we need is the range. We also wanted to know how far the particle traveled. And so if we go back to our equation 1, that we did when that we found when we were doing the x direction analysis, we had that L is equal the x component of the velocity times the time of flight. And so we have everything we need now to calculate L. So we know the 30 meters per second. We know the angle was 40 degrees. And we just found that the time of flight is 4.39 seconds. And so if we plug that all into our calculator, we can calculate that the particle travels approximately 101 meters as it flies through the air. And so that brings us to the conclusion we've been able to solve all the different parts of this problem.